Good afternoon, everyone. We are Big Horn Maritime Systems. My name is Mr. Matthew Benjamin. This is Mr. Crane, Mr. Mason Dansby, Mr. Alex Butler. Big Horn was contracted for 4 separate systems for a 3 million cubic foot LPG ammonia tanker. The 4 systems are the ship storage refrigeration system, the HVAC system, distilled water and potable water systems, and the waste management and disposal system.
The first system we're going to be covering is the ship store refrigeration system. The purpose of the system is to provide food supplies that are maintained and preserved, chilled and frozen spaces that are preserved to prevent spoilage when traveling from California to Hawaii. Additionally, the plant is requested to automatically operate based on different pressure switches on the compressor as well as the condenser. Lastly, there is required to be the adequate amount of refrigerated goods to and from California to Hawaii based on the volumetric capacity of each chilled and refrigerated spaces. The system is comprised of a 3-ton direct expansion R449A refrigerant system. There are 2 separate plants, with 1 compressor and condenser unit in each plant. One is always on operation with the other on standby for redundancy purposes. Lastly, there are 2 chilled and refrigerated spaces. There's 1 chill box with a volume of 954 cubic feet, maintained from 34 to 37 degrees Fahrenheit, and a freeze box with the same volume from 954 cubic feet, maintained from -10 to 0 degrees Fahrenheit. In terms of equipment specifics, one of the major components is the Bach semi-hermetic single-stage reciprocating compressor. This has a displacement of 30 cubic feet per minute, a refrigerant capacity of 39,200 BTUs per hour, and was selected based upon our evaporating and condensing temperatures of -13 degrees Fahrenheit and 109 degrees Fahrenheit, respectively. Next up, we selected our evaporator, which is a bone low temperature evaporator with an electric defrost heater unit. This has a refrigeration capacity of 48,000 BTUs per hour, a fan's volumetric flow rate of 7,050 cubic feet per minute, and an automatic electric defrost heater with a power draw rate of 15.1 kilowatts. Next up, we selected a Bitzer shell and tube type freshwater cooled condenser. This condenser has a capacity of 51,500 BTUs per hour, utilizes cooling freshwater from the freshwater cooling system, a volumetric flow rate of 5 cubic feet per minute, and a receiver volume of 11.3 liters. Lastly, in our system, we used a Danfoss, the externally equalized TXV valves because of the large temperature range from -40 to 50 degrees Fahrenheit, a orifice capacity to meet system requirements of 5 tons, and a adequate volumetric flow rate of 4 cubic feet per minute. Additionally, these externally equalized control valves were used because of the large pressure drops experienced within the evaporators, which are greater than 2 psi. So, next up, we're going to view the overall system schematic drawing of the refrigeration system. As you can see, we have 2 compressor condenser units, a liquid suction heat exchanger, our externally equalized TXV valves with a back pressure regulating valve on each chill box, and then our 2 evaporators for both of our refrigerated spaces. First, we're going to look at our one compressor condenser unit. This is comprised of an accumulator, which is used to accumulate moisture of the refrigerant prior to entering the compressor to prevent slugging within the compressor. There are compressor high and low pressure safety switches to automatically operate the compressor based on the pressures for the high pressure cutout for the compressor, there's a 400 psi cutout and a cut-in, which it requires to be manually reset. And for the low pressure cutout for the compressor, it's a -3 psi cutout with a cut-in at 50 psi. From there, the vapor superheated refrigerant will travel through the oil separator, a condenser, water-cooled condenser with a pressure relief valve, equipped with a pressure relief valve set at 430 psi, which is compliant with 46 CFR TAC 58. And then lastly, the receiver for repair and manual takedown of the refrigerants in the system. Next, we're going to look at the right side of the drawing. As mentioned prior, we have our liquid suction heat exchanger. This is used to subcool the liquid refrigerant prior to entering the evaporator, as well as evaporate any leftover vapor refrigerant prior to entering the compressor. 2 externally equalized TXVs and a back pressure regulating valve on the chill box to maintain humidity control within the refrigerated space.
All right, so the next aspect we're going to talk about is the refrigerant selection. This is important to any refrigerant or HVAC system, so we're going to walk through the considerations we made to different refrigerants and why we ultimately chose the refrigerant we decided. First thing we're going to look at is R134A and R404A. These are two of the most common types of refrigerants. So they are easily accessible in most parts of the globe, and they are relatively cheap compared to other refrigerants on this list. Now, the disadvantage to these, especially with R134A, is it has a high global warming potential. And for that reason, there's a likelihood of it being phased out in the near future. So we decided not to go with this refrigerant for that reason. So the next thing we're going to look at is ammonia. Now, there are a lot of old systems that use ammonia as a refrigerant. And if you don't know, it's actually coming back into fashion because ammonia has a low global warming potential. Now, while that's good, and also with the consideration that we're going to have ammonia on board as cargo, so we're already going to be prepared for some of that, the disadvantage to ammonia is it has a toxicity hazard for workers, as well as a high flammability under pressure. There's been multiple reports from both OSHA and the EPA about the hazards related to ammonia refrigerant, particularly in the marine environment. So for that reason, we decided for the safety of the crew that we were going to not use an ammonia system. Next system we looked at is R22 and R12. Now, this has a low global warming potential, believe it or not. And generally, because the systems are built in a way that's robust, they have less issues with leakage. Now, the unfortunate thing about R22 and R12 is it was made illegal to manufacture back in the 90s. Here are the related CFRs to the ozone depletion and R22 and R12. And for that reason, the prices on it fluctuate a lot and the access to it fluctuates a lot. So for that reason, we're not going to use R22 or R12. Now, before we get to our final decision, the last one we're going to talk about is R1234YF, which is a common refrigerant in the automotive industry. It has a low global warming potential as a refrigerant, but the disadvantage is it's not as energy efficient, and it's about 8 to 10% less cooling capacity per, the amount that the compressor is working. So for that reason, you're going to be burning more. You're going to have more emissions coming from your generators if you're running MDO, and even so, you're going to be running your generators more, burning through more fuel. And for that reason, we decided not to go with this refrigerant. And that brings us to our final selection, which is R449A. Now, this has several advantages. It has a good refrigeration effect. It's safe for maritime operations compared to other refrigerants. It can be used in both the HVAC and reefer systems. And most importantly, the pressures and temperatures it operates under can mean the system can be easily retrofitted to other refrigerants. And I'll get back to that in a minute. It does have some disadvantages. It is not as great a refrigerant effect as some of the other alternatives. And it's about 42% more expensive per pound than R134A. So you may ask, is that 42% worth it? Well, consider that if this refrigerant gets phased out, you can easily swap the system without swapping the entire system simply by changing a couple components. Whereas R134A, the pressures that it operates at, it's likely you're going to have to change a lot more of the components. So the next thing we're going to talk about is the HVAC system. So the HVAC system shares several component manufacturers as the refrigeration system. So we're going to talk about one of the unique aspects about it, which is the separation of the machinery space, where we have our compressor, condenser, receiver unit, as well as the air handler unit, which will be in the house. Now, we separated this out and piped it together so we can, in the machinery space, have the compressor, which will create more noise, as well as have more oil and have that compressor running in an environment that's protected by CO2. Whereas our air handler unit, which is primarily responsible for treating, heating, and cooling the air, is going to be up on the upper deck level. and there it's going to be easier to pipe in fresh or duct in fresh air from the outside, as well as have the return from the house without going down to the machinery space. And with this segregation, we can sort of get the best of both worlds. And so looking at the drawing, we're going to look at the air handler system first. As you can see, it goes through an air filter, then it goes through an electric heat coil, which can be turned on in environments where you need to heat the air on the ship. While this is not going to be common, as the ship is going to be primarily going from Long Beach to Hawaii, it is important to have the capability of heating. And then it goes through the evaporator here. This is the cooling evaporator, so that's what's going to cool the air. And it goes through a humidification unit, which uses the potable water system to humidify the air when it's necessary. And then it goes through a blower system, and then it goes through the air out to the house. All right, so that's air inlet, air filter, heating coil, evaporator, humidifier, blower, air down. And then in the engine room, we have your basic refrigeration system, which has compressor, condenser, receiver, and then goes through a filter, dryer, TXV, and then back up to the back.
The distilled water and potable water systems will serve the purpose of supplying distilled water and potable water to various systems throughout the ship. The primary components of these systems are the freshwater generator, ejector and distillate pump, the rehardening filter, silver ion sterilizer, to name a few. And the freshwater will be used in the hot and cold water accommodation service lines, deck service, expansion tank, and turbocharger cleaning supply, to name a few. Some design considerations. First, we went with the assumption of the maximum crew allowed, which would be 29 persons, and using Harrington Marine Engineering, an approximation of around 100 gallons per person per day. And the length of a trip multiplied by 2 for redundancy gives us a capacity of 40,600 gallons per each of the 2 potable water tanks, and a capacity of 13,500 gallons in the distilled water tank. The evaporator that we decided to go with is the Alpha Laval Aqua Blue type evaporator. This has a capacity of around 1,240 cubic feet per day and comes built in with a distillate pump with a flow rate of 105 cubic feet per hour and a consumed power of 1.1 kilowatts. The hot water accommodation service line will be equipped with a ZDR 0.2 electric calorifier. This unit has a storage capacity of 7 cubic feet, a heating power of 24 kilowatts, and a working pressure of around 58 psi. The outlet temperature of the freshwater will have a temperature of 150 degrees Fahrenheit. Finally, along with the distillate pump, the unit also comes with an ejector pump that has a flow rate of around 1,770 cubic feet per hour and a consumed power of 9.5 kilowatts. Lastly, we'll have the silver ion sterilizer to ensure that the potable water is fit for human consumption. This has a capacity of up to around 8,500 cubic feet per day and a lifetime of around 88,000 cubic feet. With the Hydrofor unit, we have 2 Heinrich Behrens Hydrofor pumps. Each pump has a capacity of around 175 cubic feet per day and has a consumed power of 2.2 kilowatts per pump. The regulatory compliance for these systems include ABS requirements for corrosion-resistant screens on each vent line coming from the tanks to ensure that no contaminants get inside the water, and the Coast Guard CFRs that ensure the potable water systems are completely separate from other systems so that there's no backflow or contaminants allowed into the systems. Here is the distilled water system. We will look closer at the freshwater generator itself. As you can see here, the salt water will be used as the cooling medium in the condenser part of the unit and as the means of creating a vacuum through the ejector pump. And the waste heat from the jacket water from the main engine will be used as the heating medium in the evaporator section of the unit. There's also a demister screen that removes any vapor and contaminants from the vapor before it's condensed again into fresh water. Next, we have the potable water system. We will take a closer look at the Hydrofor tank and pumps. As mentioned previously, we have 2 Hydrofor pumps and strainers that supply potable water from the tanks to the hydrofor tank. This tank will supply pressure to the accommodation lines, and this water can be sent to various lines such as drinking water or the hot and cold water accommodation as seen here.
All right, our last system is the waste management and disposal system. So the purpose of this system is to, one, store and discharge wastewater and sewage via the sewage treatment system, and two, accommodate for the storage of waste garbage on board the vessel to discharge to a shoreside facility. Some of the primary components will be the marine sanitation device, or MSD, the clean effluent discharge pump, the macerator pump, the sewage holding tank, the aerobic biomass, and the garbage compactor. So this system will be used for the shower and sink gray water, toilet black water, the collection of the galley and hospital drains, effluent discharge via the shoreside connection, or into the sewage holding tank or overboard discharge. And lastly, we also have the storage of the garbage in the garbage room. So some design considerations. We'll start with the sewage treatment plant. This unit operates for a capacity between 21 and 29 people. We estimated that per person, we'd have an estimated consumption rate of 20 gallons per person per day. And we also considered the discharge pump head to the shoreside connection. For the sewage holding tank, we have a maximum capacity of 1,400 cubic feet. With a maximum capacity crew of 29 people, if per person we have a maximum consumption of 27 gallons per day, we have a maximum storage capacity of 14 days. And with a minimum consumption rate of 13 gallons per day, we have a maximum storage of 30 days. If there are less people on the vessel, this storage, the storage range will go even higher all across the board. Next up, we also have our garbage storage. So with our garbage storage, we have designated the room on the main deck, so it has ease of access to the shore stores or provisions crane for discharge to a shoreside facility. And then for regulatory compliance, specifically for components, we have the sewage holding tank baffles, which permit holes to allow for effluent flow through the bottom of the baffles, according to 33 CFR 159.81. We also have IMO standards for the effluent discharge head. And here's a complete list for regulatory compliance. As you can see, we have MARPOL Annex 4 regulations, and we also have 33 CFR 159.5 through 309, and we also have 40 CFR 139.21. Going into equipment specifics, we have our MSD system manufactured by Gertsen and Olufsen. It's a combination to, it's a biological oxidation type unit. It has 4 compartments and has maximum capacity for 29 people. So we chose this system over other types of units. Some other units that we considered were the anaerobic process unit. This unit specifically had slower decomposition rates of sewage, had higher sludge production, and had higher methane emissions. Our second unit that we considered was the chemical treatment system. This had higher operating costs, and it generally had lower effluent quality at the discharge. And lastly, we had a third unit that we used, which was the membrane bioreactor, which used a lot of energy in its processes, and it was prone to membrane fouling. So the advantages of the biological oxidation type unit, which is what we chose, higher quality effluent, has reduced thermotolerant coliform levels, which according to the International Maritime Organization is under 35 milligrams per liter, has lower sludge production, faster decomposition, and has lower maintenance, which ultimately means lower costs. Our clean effluent discharge pump is manufactured by Ibarra. This has a maximum flow rate of 150 gallons per minute and a maximum delivery height of 60 feet. We calculated that we'd have the MSD system approximately 30 to 40 feet underneath the shoreside connection, which permits this pump to be used for our delivery height. For our macerator pump, we chose the macerator pump manufactured by Herbiner. This has a flow rate of 40 gallons per minute and a delivery height of 10 feet. This macerator pump will be located on the MSD system itself. And then we also chose the Becker air compressor, which has an airflow rate of 18 cubic feet per minute at an operating pressure of 5.8 psi. All right, and this is the total system drawing. So as you can see, toward the top here, we have our shoreside connection. Here we have our sewage holding tank, our MSD, and then our overboard discharge, as well as our saltwater in for backflowing in the system and for the sewage holding tank. We take a quick look at the MSD itself. We can see that there's 4 different compartments. Our first compartment is going to be the inlet and mixing tank, which is where the macerator pump will cycle the raw sewage for breakdown. And then we have our bioreactor. The air compressor will supply oxygen to agitate and promote faster decomposition of sewage into effluent. From here, the effluent will then go over into the settling chamber, which via density will have sludge accumulating at the bottom, scum towards the top, and our effluent towards the middle. The scum and the sludge will typically recirculate back to the bioreactor for, again, decomposition, and then which will go back to the settling chamber for further settling. After the effluent passes through the settling chamber, it goes to the the effluent discharge tank, where an ultraviolet lamp will sterilize the effluent into clean effluent, which we can either pump to a shoreside connection, to the sewage holding tank, or to our overboard discharge. Now, if we look at our collection system, here we can see our gray water and black water accommodation, our collection systems. These will go straight to the MSD system for treatment. We also have our hospital gray water and black water that will pass through our MSD system as well. And then we have our galley gray water over here, which will pass through the grease trap unless we designate it to flow through a separate line straight to the MSD. In this case, we're going to always have the galley gray water pass through the grease trap to collect any oils, fats, whatever, so we have less maintenance costs on the MSD system itself. Any questions?
Well, one quick comment, slide 32. Order back there without getting this busy. Yeah. Yeah, so on the ABS reg, a couple of comments on that. So you're using an older rule set in 2021. So there's a newer one out, and then you're missing the front half of the regulation number or the rule number. It should be 3 numbers with hyphens in between, then a slash, and then the paragraph. Right now, I don't know where to go look that up, because that could be paragraph 935 in any one of the parts or subchapter or chapters. So just as a rule of thumb, always make sure that when you're doing it, you include whatever's on the header. But same thing with Lloyd's, same thing with DNV, all that kind of stuff. Just make sure you grab what's on top of that page so you know which section or part you're dealing with, because it matters a lot. It's just like in the CFRs. If you're quoting something for a small passenger vessel when you're, really supposed to be doing, subchapter J or something like that. So it kind of matters. So just pay attention to that. That was the only real small nitpicky thing I had. Otherwise, it was a very good presentation, guys.
Thank you very much, sir. All right, now.
I just had 2 questions. Did you include, excuse me, a hot water recirculation pump for the hot water system?
Not in the system that I drew.
Okay. Why do we use those? You know why? Because you don't want somebody at the other end of the ship turning on the hot water faucet, right? Letting the water run until they finally get hot water coming out. So most ships off that hot water heater, they have a small pump and it just recirculates the water through a loop, right? And then there's branches to the different staterooms or whatever. That way, when you turn on the faucet, you get hot water because there's always hot water circulating through the system. It's a low head pump because all it's overcoming is just the friction in the system. So anyway, that's something to look at. And then the other, this is really just a comment. The multi-lobe pump that's being used as the distillate pump, is comes with that distiller? Is that correct? Or
Yes, sir. The load pump, distillate pump, and the injector pump both come with.
Okay,
the
I just thought that's an unusual selection for that particular application, but if they're supplying it, then that's fine. All right, thank you.
Thank you, sir.
Great.
7.
just a couple of things. So, I guess you zoomed in over by the evaporators, they have externally equalized TXV valve, and then to the left of that, it looks like a control valve, very hard to see in that, there you go. But I think that's a box solenoid valve.
If you're to the left of the TSV,
So, yeah,
yes, that is a box one valve. Yes, sir.
it's the wrong symbol and it's not labeled, so. And if we go to the left part of that diagram by the receivers.
Yes.
Okay, so, actually, I'd like to just see on page 7, okay, so you see the 2 receivers,
Yes.
one and 2, I guess.
Yes, sir.
All right, so they're both just connected to
Right,
each other.
no valves there. Yes, sir.
Yeah, there's no isolation
Yes, sir.
valve.
Yes, sir.
So you can't separate them. The sight glass, you have it shown on the condenser. I think that goes on the receiver.
Yes, sir.
Okay, now what happens with those is, one of them's going to be in service, the other's probably going to be isolated and secured.
Right. Yes, sir.
So what happens there is the pressure inside that receiver is dependent on the ambient temperature, which in the case of a fire, could build up a extremely high pressure on that receiver and explode it. So there would be a relief valve fitted on that. Yeah. And then what they do is you don't want any of that stuff leaking out. So there would be a burst disc on the outlet of that. It's just, the flow diagram is like really awesome. It's just missing some of these details here. So that was, you used, it's funny, you used a funny font, so it's capital lowercase, but let's go to just page 33 for just a couple of workmanship type things. I'll try to make this fast, but if you look at the text, like, first off, the text is varying quite a bit all over the place. It's, you're using the old TXT font, which is a default in AutoCAD, just terrible font.
Yes, sir.
And I would just probably define your standard font as Roman S, so it's a tree type font nowadays, good for making PDFs and things. But and that's classic mechanical font, close enough to it. And then you use an upper and lower case. In the line weighting, I would refer you to look at the Harrington textbook on the piping systems, because they show bold lines and then finer equipment lines, and it makes things just pop and stand out and it's easier to read. Over there you have on the left side, there's an arrow going down, it just says 2 hydrophore.
This one, sir?
Yeah.
Yes, sir.
Okay, normally what you would do with engineering drawings like this is you would use an arrow convention that would define what drawing you would find that hydrophore tank. So you'd be able to relate this drawing to other drawings and have it linked together. And this is like common on all these drawings this year. There's no interrelationship between one system relating to somebody else's system. It's like cooling water on one system and whatever refrigerant on another system. There's no interrelationship between those systems.
Right, understood.
Let's see. And the last group, I meant to point this out too. They spelled separator with 2 E's. That just, I don't know why that grates on me. It just drives me insane. You didn't drive me insane, but you misspelled handler all over the place. It's handler, not handler. Because it appears in like 15 places here. Okay, so just you should just try to proofread that stuff because it's just things that can be avoided.
Yes, sir.
Run spell check. I think even AutoCAD is spell check. But nice job. I definitely like the. Oh, and the other thing that I found odd. I just find it odd. And I do have to point it out because it just looks like too odd. But there's I can't find the page. There's a distillate pump, and it looks to be like a lobe type pump.
Yes, sir, that's the one that comes with the alpha Laval unit.
That's what they use in
Yes, sir.
That was what you asked.
Yeah, I don't think it's unusual.
Right, it is unusual.
You know, thinking a low pump, you have to have timing gears, right? So now you've made the machine a lot more complex than it would need to be if it was just a simple centrifugal pump.
Or even like a regenerative turbine pump or something. Okay.
I believe when we did the cost estimate in the full report, it was cheaper to use the full Alpha Laval system rather than kind of cherry pick several different components.
No, I think if they're supplying it as part of their
Right.
system, then that's fine, because if you say, well, no, we're gonna use something else, and then you have a problem, they're gonna say, well, it's the pump you picked. If
Yeah,
you use our pick, the
exactly.
pump, it would have worked fine.
Exactly.
So that's another, can of worms you don't need to open up, but it's unusual to use that type of pump in that application.
I think you guys heard that before, right? During a practice presentations? Yeah, they've heard this thing about the low pump quite a bit over the past couple of weeks.
That's good.
I had the answer loaded the whole time.
Yeah, thank you, thank you.
Brock. You're up, Brock.
All right. So a couple questions, guys. So actually, if you go to slide 32, I'm gonna applaud you on finding the potable water system regulations. So good job, guys. All right, go to 42. Almost there. All right, cool. So the U.S. is actually not signatory to MARPOL Annex 4. That's why we have 33 CFR 159. So just recommend deleting that. And then is your sewage treatment plant type approved?
Yes, sir.
Coast Guard type? Yeah, okay. Just list it. List the type approval number when you get it. Other than that, that is all. Thank you guys. Appreciate it. Great job.
Any other questions?
Nobody has any more questions? All right, guys, thank you very much.